Tonight, we are going to travel very far without leaving your bed. Close your eyes, breathe slowly, and let your body soften and rest. Imagine the night sky, full of quiet stars. Each one of those stars is a sun, and some of them carry deep and gentle stories. One of those stories is about black holes. A black hole is not a monster, and it is not something that needs to scare you. It is simply a place in the universe where gravity is extremely strong, so strong that even light cannot escape. And yet, everything happens in silence, slowly, calmly, as if space itself were resting. To understand a black hole, imagine a giant star, much larger than our sun. For millions and millions of years, that star shines and warms, giving light to the worlds around it. But eventually, the star becomes tired. Its fuel runs out, like a candle finishing its flame. The star begins to shrink, smaller and smaller, its weight pressing inward, until all of it is concentrated into an incredibly tiny point. That tiny point is the heart of a black hole. Around it, space bends softly, like a blanket sinking under something heavy. Anything that comes too close begins to slowly swirl, like leaves drifting in a gentle whirlpool. Nothing feels violent. There is no sound, only silence and a soft darkness. Scientists call a special boundary the event horizon. It is an invisible limit. If something crosses it, it cannot return. But from far away, a black hole simply looks like a dark sphere surrounded by light that spins slowly around it. You can imagine yourself floating safely far from it, just watching, drifting peacefully in space, feeling sleep coming closer, like a quiet wave. As you rest here, remember that black holes are not chaos. They are part of the universe's rhythm, part of its long and peaceful story. Everything in the cosmos forms, changes, and rests again. And while you listen, your mind can do the same, slowly settling, gently drifting, softly falling asleep. Space extends in every direction, dark and calm, filled with distant stars. In that vastness, a black hole can rest quietly, with a faint ring of light around it. Its presence is steady and ancient. Black holes are interesting because they change how space and time behave. You can imagine space as a soft fabric. When something heavy is placed on it, the fabric bends. A black hole is simply a place where the bend becomes very deep. There is no intention in it. It is gravity following its own rules, shaping the universe in silence. Around many black holes, there is a bright ring called an accretion disk. It is made of gas and dust moving in circles. As the material heats up, it glows, creating a soft halo of light around a dark center. The contrast looks calm rather than violent, because everything happens on very large time scales. Some black holes come from single massive stars that collapsed long ago. Others are much larger and are called supermassive black holes. They stay in the centers of galaxies. Our Milky Way has one of these giants. Stars move around it in wide orbits, like dancers tracing huge circles over millions of years. Near a black hole, time does not behave exactly as it does far away. Clocks close to it seem to run more slowly. This change is gradual, not sudden, just as day slowly becomes night. Black holes do not break the laws of the universe. They reveal how flexible those laws truly are. If an object gets too close and passes the event horizon, it can no longer return. From the outside, it appears to fade and slow, as if time stretches near the edge. There is no sound. Space simply continues its motion, and the object becomes part of the region around the black hole. Rather than being only destructive, black holes are part of cosmic balance. They help organize the centers of galaxies and influence how stars move. They show that darkness also has structure, order, and a quiet beauty. Black holes invite questions. What are they exactly? Are they objects? Are they places? Or are they conditions of space and time? When we ask these questions, we begin to see how many ideas exist around them. The most accepted view in science is that a black hole is a region where matter has been compressed into an extremely small volume. Gravity there is so strong that nothing can escape once it gets too close. This idea comes from Einstein's theory of general relativity. According to it, mass tells space how to curve, and curved space tells matter how to move. A black hole is a place where this curvature becomes extremely intense. Scientists also wonder what lies at the very center. Equations suggest something called a singularity, a point of enormous density where our current physics cannot fully describe what happens. Is this singularity real? Or is it a sign that our theories are incomplete? Some researchers think quantum physics, which describes the tiniest particles, might soften the singularity and replace it with something more spread out. Another question is whether black holes truly erase information. When something falls inside, is every detail about it lost forever? This is called the information paradox. One idea is that information could be stored on the surface of the event horizon in a thin layer that we do not yet fully understand. Another idea is that information may leak out extremely slowly through faint radiation over very long periods of time. There are also questions about what happens from the point of view of something that falls in. Does space continue inward like a tunnel? Could there be bridges to distant regions of the universe called wormholes? For now, these ideas remain theoretical. They are guiding questions that inspire new research even without final answers. As we ask what black holes are, how they begin, and what they contain, we find something important. Black holes are not only physical objects. They are also invitations to think. They remind us that the universe is vast and mysterious, and that curiosity is a natural way to explore it. A natural question about black holes is whether they last forever. For many years, scientists thought they would simply remain, slowly growing as they pulled in nearby matter. Then came the idea of Hawking radiation, proposed by Stephen Hawking. It suggests a black hole might slowly lose energy and become smaller over extremely long periods of time. The central idea is that empty space is not completely empty. On very small scales, tiny pairs of particles appear and disappear. Near the event horizon of a black hole, one particle of the pair can fall inward while the other escapes into space. The escaping particle carries away a small amount of energy. From far away, this looks like a very faint glow. For large black holes, the process is incredibly slow. For very small ones, it would be faster. This means that in the distant future, a black hole could gradually evaporate. This raises further questions. If a black hole fully evaporates, what remains at the end? Does the information about everything that fell inside disappear, or does it return in some changed form? Or is the final stage still beyond what our current physics can clearly describe? These questions connect gravity with quantum theory and with the study of heat and energy, bringing together fields that are usually separate. We can also ask how we know black holes exist if no light escapes from them. The answer comes from their effects on other objects. We see stars moving in tight orbits around invisible centers that must be extremely massive. We detect ripples in space and time produced when huge objects collide, signals that match the merging of black holes. Astronomers have also created images of a dark central shadow surrounded by a bright ring using networks of radio telescopes on Earth. Each observation increases confidence, but also invites new puzzles. Black holes stand between theory and observation and show how careful study can reveal hidden parts of the universe while still leaving room for mystery. Black holes are not all the same. Scientists group them by size and by how they form. The smallest confirmed type is called a stellar black hole. It forms when a massive star uses up its fuel and its core collapses under its own gravity. The outer layers are blown away and the core becomes a compact region with gravity so strong that light cannot escape. Much larger are supermassive black holes. These sit quietly in the centers of galaxies, including the Milky Way. They contain the mass of millions or even billions of suns. How did they grow so large? One idea is that many smaller black holes slowly merged over time. Another idea is that large clouds of gas in the early universe collapsed directly into huge black holes without passing through the stage of single stars. There is also the idea of intermediate mass black holes. They would be between the stellar and supermassive types. Evidence for them is growing. For example, when we see strong X-ray sources in star clusters, or when gravitational wave detectors record mergers of heavy compact objects. They may form when many stars interact in crowded regions and gradually sink together. Some theories even suggest microscopic black holes. These would be tiny and short-lived, maybe formed in the very early universe when conditions were extremely dense and hot. None have been confirmed, but the idea helps scientists test the limits of current physics and think about how gravity behaves at very small scales. By comparing these different kinds of black holes, we learn about the history of the universe. We see how stars live and end, how galaxies are shaped, and how matter can collect in quiet but powerful centers. Each type adds another piece to the picture, showing that black holes are not a single simple object, but a whole family of related cosmic structures. What would it be like near a black hole? Not inside, just nearby. The picture is very different from the dramatic scenes in movies. There is no sudden pulling or loud tearing sound. Gravity simply becomes stronger as you get closer, and space and time curve more noticeably. Close to a black hole, matter often forms a thin rotating disk. This disk is made of gas and dust slowly spiraling inward. Friction inside the disk heats the material and makes it glow. That is why black holes are often surrounded by bright light, even though the black hole itself does not shine. The light comes from matter in motion, not from the black hole. Sometimes powerful jets of particles are launched from the regions around supermassive black holes. They are not coming from inside the black hole. They are created by magnetic fields and fast-moving plasma near the disk. These jets can travel vast distances through space and can even shape the gas in entire galaxies. Another interesting effect near a black hole is gravitational time dilation. A clock far away and a clock near the black hole will not agree. The one closer to the black hole will run more slowly. This is not just an idea. It follows from general relativity and has been tested in weaker forms near Earth using very precise clocks. There is also the stretching of objects moving toward the black hole. Gravity is slightly stronger on the side closer to the black hole than on the side farther away. This difference can stretch an object along the direction of motion. In extreme cases, scientists call this tidal stretching. It is simply gravity acting unevenly across distance. Even with these strong effects, the region outside the event horizon is still governed by known physics. Equations describe the orbits of objects, the heat of the accretion disk, and the bending of light. Black holes are strange, but they are not chaos. They are lawful parts of the universe, showing us what gravity can do when it is allowed to work at its strongest. The idea of black holes appeared before we could observe them. Long ago, some scientists asked a simple question. What happens if a star is so massive that even light cannot escape from it? They did not use the name black hole yet, but the seed of the concept was there. Later, Einstein's theory of general relativity provided the tools to describe curved space and time. Soon after, mathematicians studying his equations found solutions that described extremely compact objects with a region from which nothing can return. At first, many scientists thought these were only mathematical curiosities. They seemed too strange to exist in nature. Over time, the picture changed. Astronomers found stars that moved as if they were orbiting invisible companions much heavier than any normal star. They saw X-rays coming from regions where material seemed to fall into something compact and very dense. Slowly, the idea that black holes were real objects in the universe became more and more convincing. Today, the concept is central to astrophysics. What began as a question in equations is now linked to observations across many wavelengths of light and to measurements of gravitational waves. It shows how theory and observation can grow together, each one supporting the other in understanding the universe. Even though black holes do not emit light, we have several ways to study them. One way is by watching how nearby stars move. If a star orbits very quickly around something invisible, the mass of that unseen object can be calculated. When the mass is too high to be a normal star, a black hole is the most reasonable explanation. Another way is by detecting high-energy radiation from material in the accretion disk. As gas spirals inward, it heats up and emits X-rays. Telescopes that see X-rays reveal bright spots in the sky where compact objects are feeding on surrounding matter. Many of these sources are strong candidates for black holes. We also observe black holes through gravitational waves. When two massive black holes merge, they create ripples in space and time that spread outward. Instruments on Earth have detected these signals, matching the predictions of relativity. Each detection provides information about the mass and spin of the merging black holes. Finally, radio telescopes combined across the planet have produced images of the shadow of a black hole against its glowing surroundings. This is not a direct picture of the interior, but a map of how light bends around extreme gravity. It is strong visual evidence that these objects truly exist. At the heart of many galaxies, there is a supermassive black hole. The Milky Way has one called Sagittarius A. It is millions of times more massive than the Sun. Stars near the center of our galaxy move in fast curved paths, showing that something extremely heavy is there. These central black holes do more than simply sit in place. They can influence the shape and growth of their galaxies. When large amounts of gas fall toward them, powerful radiation and jets can be produced. This energy can heat surrounding gas and slow the formation of new stars. In this way, black holes and galaxies co-evolve, each affecting the other. Not all central black holes are active. Many are quiet, taking in little material and producing little radiation. Even then, they hold together the crowded regions around them, acting as massive anchors in the centers of stellar systems. By studying these supermassive black holes, we also learn about the early universe. To reach their present size, they must have grown rapidly when the universe was young. Understanding that growth helps us understand how the first galaxies formed and how structure appeared on cosmic scales. At the heart of many galaxies, there is a supermassive black hole. The Milky Way has one called Sagittarius A. It is millions of times more massive than the Sun. Stars near the center of our galaxy move in fast curved paths, showing that something extremely heavy is there. These central black holes do more than simply sit in place. They can influence the shape and growth of their galaxies. When large amounts of gas fall toward them, powerful radiation and jets can be produced. This energy can heat surrounding gas and slow the formation of new stars. In this way, black holes and galaxies co-evolve, each affecting the other. Not all central black holes are active. Many are quiet, taking in little material and producing little radiation. Even then, they hold together the crowded regions around them, acting as massive anchors in the centers of stellar systems. By studying these supermassive black holes, we also learn about the early universe. To reach their present size, they must have grown rapidly when the universe was young. Understanding that growth helps us understand how the first galaxies formed and how structure appeared on cosmic scales. Even with all we know, many questions remain. What truly happens at the center of a black hole? Is there a real singularity, or does quantum physics change the picture at very small scales? We do not yet have a complete theory that unites gravity and quantum mechanics, so the final answer is still open. Another question is about information. When matter falls into a black hole, is every detail about it lost forever? Or is the information somehow preserved in subtle ways on the event horizon or in the radiation that escapes as the black hole slowly evaporates? This is one of the deepest puzzles in modern physics. We also wonder whether black holes could be connected to other regions of space through theoretical tunnels, sometimes called wormholes. There is no observational proof for this, but the idea helps scientists test the limits of our theories and think creatively about space and time. Black holes stand at the edge of our understanding. They challenge our intuition and encourage new ideas. By asking questions about them, we are also asking questions about the nature of reality itself, about space, time, matter, and energy on the largest scales we can imagine. Black holes are closely connected with the idea of time. General relativity tells us that gravity and time are linked. Where gravity is strong, time passes more slowly compared with regions where gravity is weaker. Near a black hole, this effect becomes extreme and makes time behave in ways that feel almost magical. Imagine two observers. One stays far from the black hole. The other travels closer to the event horizon. For the distant observer, the clock near the black hole appears to tick more slowly. Signals coming from the traveler seem stretched. For the traveler, however, their own clock feels normal. They experience time in the usual way, second by second, without noticing anything unusual about their personal flow of time. This difference is called time dilation, and it shows that time is not absolute. It depends on gravity and on motion. Black holes provide the strongest natural laboratories for this effect. Even though we cannot go there ourselves, our equations and observations near other massive objects confirm that this strange behavior of time is real. The link between time and gravity raises deep questions. Is time something that flows independently, or is it part of the geometry of the universe, shaped by mass and energy? Black holes suggest the second idea. They show that time is woven together with space into a single flexible structure that can bend, stretch, and slow under the influence of gravity. By studying black holes and their influence on time, scientists hope to learn more about the early universe and about the ultimate fate of cosmic structures. Time near a black hole is not just a curiosity. It is a clue to the deeper rules that govern reality on every scale. The event horizon marks the boundary of no return. Once something passes inside, it cannot escape back to the outside universe. Light cannot come out, signals cannot come out, and paths through space all point inward. Yet the region inside is not chaotic noise. It is still governed by the laws of gravity. From the outside, an object falling toward the horizon seems to slow down and fade as its light becomes weaker and more red. To the falling object itself, however, the crossing happens in finite time. There is nothing physically special at the horizon in terms of local sensation. The true mystery lies deeper inside, closer to the theoretical singularity where densities become extremely large. Our best current theories disagree about what happens in the deepest interior. Classical general relativity predicts a singularity. Quantum physics suggests that such a point might be replaced by something more spread out and finite. Some ideas propose that space and time may change their nature at very small scales, preventing infinite density from forming. Because no signal from inside the horizon can return, the interior remains hidden from direct observation. We explore it through mathematics, computer simulations, and indirect effects on the outside universe. The interior of a black hole reminds us that there are regions of the cosmos that cannot be fully seen, only inferred through their influence and through careful reasoning. Black holes do not only affect light, they also affect the very fabric of space. When two black holes orbit each other, they gradually lose energy by sending out ripples through space and time. These ripples are called gravitational waves. They travel outward in all directions at the speed of light, carrying information about the motion and mass of the black holes that created them. In 2015, scientists directly detected gravitational waves for the first time using very sensitive instruments on Earth. The pattern of the signal matched the merger of two black holes far away. Since then, many more events have been recorded. Each detection is like hearing the universe rather than seeing it. Gravitational waves allow us to study black holes in a new way. We are not limited to the light from surrounding matter. We can measure the shaking of space itself as massive objects collide and merge. From these signals, we learn the mass, spin, and sometimes even the approximate distance of the black holes involved. This new window on the universe confirms predictions of general relativity with impressive precision. It also opens paths to discover previously unknown types of objects. Black holes, through gravitational waves, have become tools for exploring regions of the cosmos that cannot be studied by light alone. Black holes are not only features of the present universe. They may also hold clues about its earliest moments. Soon after the Big Bang, matter and energy were extremely dense and hot. Under such conditions, small regions might have collapsed under their own gravity and formed what are called primordial black holes. If such primordial black holes exist, they could vary widely in size. Some would be tiny and might already have evaporated through Hawking radiation. Others could survive to the present day and move silently through space. They might even make up part of the mysterious dark matter that influences galaxies without emitting light. This idea is still under study and not yet confirmed. The early universe would also have helped seed the growth of supermassive black holes. Young galaxies contained dense gas clouds that could collapse rapidly. The first stars were very massive and could produce black holes that later merged and accreted more material. By tracing this growth, scientists hope to understand how the giant black holes we see today reached their enormous masses so quickly. Studying black holes in the context of the early universe links cosmology, particle physics, and astrophysics. It shows that these objects are not isolated curiosities, but participants in the long story of cosmic evolution. Black holes live both in science and in imagination. They appear in movies, novels, and art as symbols of mystery, danger, or transformation. While popular images are often exaggerated, the true science is in many ways even more remarkable. Reality does not need decoration to be astonishing. They challenge common ideas about space, time, and matter. They show that light can be trapped, that time can slow, and that space can bend into shapes that our senses were not built to perceive. These features make black holes powerful tools for teaching and for inspiring curiosity in people of all ages. At the same time, black holes remind us of the limits of knowledge. There are questions we cannot yet answer and regions we cannot directly observe. Rather than being discouraging, this uncertainty invites exploration. Science grows by confronting such frontiers with patience and creativity. Black holes therefore connect rigorous mathematics, precise observation, and human wonder. They are part of the physical universe and part of our cultural universe as well. By thinking about them, we also think about our place in the cosmos and about the desire to understand that has guided humanity for generations. Black holes are not only massive objects in space. They are also deep meeting points where many areas of physics come together. Instead of asking only what they are, we can ask how they behave as physical systems. This leads to an unexpected idea. A black hole has temperature, entropy, and can even radiate energy, concepts that belong to thermodynamics as much as to gravity. The temperature of a black hole is extremely low for large masses and higher for very small ones. This means that large black holes barely radiate at all, while small ones would radiate much more strongly. Although this radiation is far too weak to detect directly from astrophysical black holes, the theory behind it connects gravity with quantum mechanics in a profound way. Entropy is a measure of how many microscopic arrangements correspond to a macroscopic object. For ordinary matter, entropy depends on volume. For black holes, entropy is proportional to the area of the event horizon. This surprising relation suggests that the information describing what has fallen into the black hole may somehow reside on its surface rather than in its interior. This idea led to the development of the holographic principle, which proposes that the full description of a region of space can be encoded on a lower dimensional boundary. The holographic view changes how we think about space itself. It implies that what we experience as three-dimensional could be connected to information stored in two dimensions. Black holes are not just objects, but potential screens on which the universe writes information in a way we do not yet fully understand. This is not science fiction. It arises from precise mathematical relationships discovered by theoretical physicists. The information paradox grows from this context. Quantum theory insists that information about a physical system is never destroyed. If a black hole eventually evaporates through radiation, what happens to all the information about the matter that fell inside? Does it vanish? Or is it encoded in delicate correlations in the outgoing radiation? Many researchers now believe that information is preserved, but how this happens in detail remains an active and subtle problem. Another area where black holes reveal new physics is in their rotation. Most astrophysical black holes are expected to spin. A rotating black hole drags space and time around with it in a process called frame dragging. Near it, space itself is twisted, and no object can remain completely still with respect to distant stars. This effect changes the shapes of orbits, the structure of accretion disks, and the energy that particles can gain near the black hole. Rotation is also linked to the enormous jets seen in some galaxies. Magnetic fields, anchored in the rotating disk and influenced by the spinning black hole, channel particles into narrow beams. These jets transport energy across vast distances and can regulate the growth of galaxies by heating surrounding gas. Black holes therefore play an organizing role in galactic ecosystems rather than acting as isolated sinks of matter. Gravitational lensing is another powerful consequence of strong gravity. Light passing near a black hole follows curved paths, and this bending acts like a natural lens. It can create rings, arcs, and multiple images of background objects. By studying these distortions, astronomers can estimate the mass and spin of the lensing black hole. The shadow images produced by large radio telescope arrays are practical examples of this phenomenon, mapping how light is swallowed or deflected at the threshold of no return. The study of black holes is increasingly driven by simulations. Supercomputers solve Einstein's equations numerically to follow the merging of black holes, the turbulence of accretion disks, and the launching of jets. These simulations predict the precise gravitational wave signals detected on Earth and guide the interpretation of observations. They also allow scientists to test alternative ideas about gravity and to see how small changes in theory would alter observable results. Black holes also connect to the question of dark matter and dark energy. While black holes cannot by themselves account for all dark matter, their presence and growth history are influenced by it. The expansion of the universe, driven by dark energy, affects how often black holes meet and merge. Thus, black holes act as tracers, helping scientists probe components of the universe that cannot be seen directly. Future observatories will deepen this picture. Space-based gravitational wave detectors will be able to listen to mergers of supermassive black holes across the universe. More sensitive radio telescopes will sharpen images of black hole shadows and allow movies of matter swirling near the horizon. High-energy observatories will study the flickering light from disks to map turbulence and magnetic fields. Open questions remain central. What is the true nature of the core? How exactly is information preserved? Is space-time smooth at the smallest scales or made of discrete elements? Are there new particles or fields that influence black hole evaporation? Each question pushes physics toward a more unified theory that includes both gravity and quantum mechanics. Black holes also play a role in the life cycle of elements. When matter is torn apart and heated near them, nuclear reactions and particle acceleration occur. Jets can seed intergalactic space with high-energy particles, influencing gas clouds that later form stars and planets. In this indirect way, black holes contribute to the environments from which future solar systems arise. Even without repetition of earlier basics, the story of black holes remains rich. They are bridges between theory and observation, between the very large and the very small. They reshape light, time, and space while obeying strict mathematical rules. They are not simply destructive objects, but key participants in the structure and evolution of the cosmos. To think about black holes is to think about fundamental questions. What is reality made of? How far do the laws of nature extend? Where do our current theories break down, and what new ideas are waiting beyond that boundary? Black holes stand quietly in the universe, yet they pull our curiosity toward them with a strength comparable to their gravity, inviting us to keep asking and keep exploring. Black holes are not only objects to be described, they are also tools for testing the deepest laws of nature. One key idea is the no-hair principle. It says that a black hole in the end is fully described by only a few numbers, mainly its mass and spin, and possibly electric charge. All the complex details of the matter that formed it are lost from the outside description. If this principle is exactly correct, then all black holes with the same mass and spin should look identical from the outside, no matter how they were formed. This idea can be tested by observing gravitational waves. When two black holes merge, the final black hole vibrates and settles into a stable shape. The pattern of those vibrations is predicted by general relativity. By comparing observations with predictions, scientists test whether real black holes follow the no-hair principle or whether tiny deviations hint at new physics. Another rich field of study involves tidal disruption events. Sometimes a star wanders too close to a massive black hole. The difference in gravity between the near and far sides of the star becomes so strong that the star is torn apart. Half of its material is flung outward. The other half spirals inward and forms a brief, very bright accretion flow. These events create powerful bursts of light across many wavelengths and let astronomers watch black holes interacting directly with stars. Black holes also play an important role in what is called feedback. When gas falls toward a supermassive black hole and becomes part of an active galactic nucleus, radiation and jets flow outward. This energy can push gas out of the galaxy or heat it so that it cannot easily collapse to form new stars. In that way, black holes regulate how quickly galaxies grow. Observations show a strong link between the mass of a galaxy's central black hole and the motion of stars in the galaxy's bulge, a relation known as the M-sigma relation. This link suggests that galaxies and their central black holes evolve together. Another question concerns the distribution of black hole masses. There seems to be a gap between the masses of the heaviest neutron stars and the lightest confirmed black holes. This mass gap may tell us something about how stars explode or collapse. It might also be filled by objects that are rare or difficult to detect. Gravitational wave observations are beginning to map this landscape, revealing black holes heavier than we expected from single stars and suggesting that some may be formed from earlier mergers. Scientists also aim to measure black hole spin. Spin affects the shape of space-time near the horizon, the efficiency of accretion, and the strength of jets. It can be estimated from X-ray spectra, especially from the broad iron emission lines that are distorted by gravity near the black hole. Time delays between changes in the inner disk and reflections from surrounding gas, a method called reverberation mapping, also provide clues about spin and disk structure. Black holes are linked not only to astrophysics, but also to quantum ideas such as entanglement. Some researchers have suggested that space-time connections, possibly resembling wormholes, may be related to patterns of quantum entanglement between particles. One slogan that captures this thought is ER equals EPR, meaning that Einstein, Rosen-Bridges, and Einstein, Podolsky, Rosen entanglement might be two ways of talking about the same underlying structure. These ideas are highly theoretical, but they indicate how black holes drive new thinking about the relationship between geometry and information. There are also alternative objects that might mimic black holes. These include gravastars, boson stars, or other exotic compact objects predicted by speculative theories. They would have no event horizon but would be extremely compact. Careful observation of gravitational waves and black hole shadows might eventually distinguish real black holes from these mimics. For now, all data are consistent with the existence of true black holes as predicted by general relativity. Observational technology is advancing quickly. The Event Horizon Telescope that produced the first images of black hole shadows is being upgraded to include more telescopes, better sensitivity, and possibly space-based elements. Future images may show motion in real time, letting us watch hot spots orbit near the event horizon. Gravitational wave detectors are also being improved, and new space-based detectors will be able to pick up signals from enormous black holes merging at the centers of galaxies across the universe. Black holes can teach us about high-energy particle acceleration. Near them, magnetic fields twist and reconnect, creating natural particle accelerators far more powerful than anything on Earth. These regions may be responsible for some of the highest energy cosmic rays that strike our planet. They also produce flickering light that varies on short timescales, revealing turbulence and structure near the horizon. Looking even further into theory, some physicists have proposed that the event horizon might not be perfectly smooth. Ideas such as firewalls or quantum fuzzball states suggest that quantum effects could alter the horizon at very small scales. If true, this might produce small echoes in the gravitational waves after black hole mergers. Searches for such echoes are ongoing, and although results are not yet conclusive, they show how black holes are used to test quantum gravity ideas that cannot be reached in laboratories. Finally, black holes deepen our sense of perspective. They show that the universe contains regions where familiar intuition fails, yet mathematics continues to work. They demonstrate that darkness can be structured, that silence can contain information, and that extreme conditions obey precise laws. By studying them, scientists are not merely cataloging objects in space. They are tracing the outlines of new physical principles that may one day unify our understanding of nature. Black holes, in this sense, are both destinations and beginnings. They mark the limits of current theories and at the same time open doors to new ones. Each observation, each signal, and each idea adds to a growing picture in which gravity, information, and quantum mechanics are not separate subjects, but pieces of a single story written across the cosmos. Black holes are described mathematically by exact solutions of Einstein's equations. The simplest one, for a non-rotating, uncharged black hole, is called the Schwarzschild solution. It predicts an event horizon whose radius is proportional to the mass. This radius is called the Schwarzschild radius. A useful rule of thumb is that a black hole of 1 solar mass has a radius of about 3 kilometers. A black hole of 10 solar masses has a radius of about 30 kilometers. A supermassive black hole of 4 million solar masses, like Sagittarius A** in our galaxy, has a radius of about 12 million kilometers, comparable to the size of Mercury's orbit. Black holes also have spin. The solution that describes a rotating black hole is called the Kerr solution. In this case, the horizon becomes flattened, and there is a region outside it called the ergosphere. In the ergosphere, no object can remain at rest relative to distant space. Rotation drags space-time itself. Energy can even be extracted from a rotating black hole through a process called the Penrose process, or through magnetic fields in the Blandford-Znajec mechanism, which is thought to power many astrophysical jets. Observations provide concrete measurements. The mass of Sagittarius A** is measured from the orbits of nearby stars with high precision. Some of these stars complete an orbit in about 16 years and come within light days of the center. Their motion shows that a compact object of about 4 million solar masses is present, confined within a region smaller than our solar system. No known cluster of normal stars or stellar remnants could be this dense without collapsing, making a black hole the only realistic explanation. The first direct image of a black hole shadow, released in 2019, showed the supermassive black hole in the galaxy M87. Its mass is about 6.5 billion times that of the Sun. The ring of light in the image corresponds to gas orbiting near the last stable orbit allowed by relativity, while the dark central region is the shadow created by light falling through the horizon. The diameter of this ring matched theoretical predictions with impressive accuracy, providing strong evidence that general relativity holds even in very strong gravity. Gravitational wave astronomy has added precise numbers. The first detected signal, GW150914, came from two black holes of about 36 and 29 solar masses merging into one of about 62 solar masses. The missing mass was emitted as pure gravitational wave energy, equivalent to roughly 3 suns converted entirely into radiation in a fraction of a second. Later events have revealed black holes ranging from a few solar masses to over 100, showing a population that was not previously known. The temperature of a black hole, according to Hawking's formula, is inversely proportional to its mass. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvin, far colder than the cosmic microwave background radiation of 2.7 Kelvin. This means that astrophysical black holes actually absorb more radiation from the universe than they emit. Only extremely tiny hypothetical black holes would radiate strongly. The time for a solar mass black hole to evaporate completely through Hawking radiation is on the order of 10 years, vastly longer than the current age of the universe. Accretion disks around black holes reach very high temperatures. In stellar mass systems, the inner disk can reach millions of degrees, emitting X-rays. In supermassive black holes, the temperatures are lower per particle, but the total luminosity can be enormous. Quasars powered by accretion onto supermassive black holes can outshine entire galaxies. Some quasars are seen at distances corresponding to less than 1 billion years after the Big Bang, showing that extremely massive black holes already existed very early in cosmic history. Timing measurements add more concrete detail. Variability in X-ray and optical light from active galactic nuclei occurs on timescales of hours or days. Because nothing can vary faster than light can cross the emitting region, these timescales give upper limits on the size of the central engine. The short variation times imply that the energy originates in very compact regions consistent with black holes rather than from extended star clusters. Black holes can also be weighed by their effect on gas. Spectra of orbiting gas clouds show Doppler shifts that reveal orbital speeds. In some galaxies, gas near the center moves at thousands of kilometers per second around an unseen mass. From these velocities and distances, Newton's and Einstein's laws yield the mass of the central black hole. These measurements agree with those from stellar orbits and from gravitational waves, producing a consistent physical picture. Looking ahead, space-based detectors such as LISA will be able to observe mergers of supermassive black holes with extreme precision. These signals will test relativity in regimes of strong gravity that cannot be reproduced on Earth. They will also trace the growth history of black holes across cosmic time, telling us when galaxies merged and how their central black holes combined. At the smallest scales, quantum gravity remains uncertain. Some approaches, such as loop quantum gravity or string theory, predict that the classical singularity is replaced by a finite structure. Others propose remnants that survive the evaporation process. None of these ideas have yet been confirmed, but they provide clear, testable predictions for future observations and experiments. By moving from general description to concrete numbers, black holes become less like abstract mysteries and more like measurable parts of the universe. Their masses, sizes, spins, and temperatures can be estimated. Their mergers shake spacetime. Their shadows can be imaged. They are extreme, but they are not beyond science. They are now among the best studied and most precisely characterized objects in modern astrophysics. Black holes are surrounded by regions where specific orbits are no longer possible. One important distance is the innermost stable circular orbit, often called the ISCO. For a non-rotating black hole, this orbit lies at 3 times the Schwarzschild radius. For a rapidly spinning black hole, the ISCO moves closer to the horizon. This difference changes how efficiently matter can release energy when it falls in. Fast-spinning black holes can convert up to about 40% of the falling mass energy into radiation, while non-rotating ones convert only about 6%. For comparison, nuclear fusion in stars converts less than 1% of mass into energy. Concrete limits also exist for stars that collapse. The Tolman-Oppenheimer-Volkoff limit describes the maximum mass of a neutron star, somewhere around 2 to 3 solar masses. Above that mass, no known pressure from neutrons can support the star against gravity, so collapse to a black hole becomes unavoidable. This limit is supported by measurements of massive neutron stars and by the masses of black holes observed in gravitational wave events. Black holes can form not only from single stars, but also from stellar mergers. When 2 neutron stars merge, the result can be a heavier neutron star or a black hole, depending on total mass. The famous event GW 170817 produced both gravitational waves and light from a kilonova explosion. The final compact object is thought to have collapsed into a black hole after briefly existing as an ultramassive neutron star. These multi-messenger observations, combining gravitational waves and electromagnetic light, allow scientists to follow the full life cycle from merger to black hole formation. Precise measurements of Sagittarius A** and M87* show differences tied to mass. Sagittarius A* is relatively quiet and variable on timescales of minutes, reflecting its smaller size, since light crosses its horizon in tens of seconds. M87*, billions of times more massive, varies much more slowly because the physical scale is so much larger. Time near black holes scales with mass, so the bigger the black hole, the slower its nearby environment appears to change. Black holes also influence their surroundings through winds. Not all infalling gas reaches the horizon. In many systems, a large fraction of the material is blown away before crossing the event horizon. These outflows enrich the surrounding galaxy with heavy elements and regulate the rate of accretion. Simulations show that turbulence, magnetic fields, and radiation pressure combine to produce complex flows that shape the environment around the black hole. The distribution of known stellar mass black holes in the Milky Way is becoming clearer with surveys from X-ray telescopes and optical missions such as Gaia. Their typical masses cluster between 5 and 20 times the mass of the Sun, though heavier examples have been found by gravitational wave detectors. Their spins vary widely, with some rotating close to the theoretical maximum. indicating growth by steady accretion rather than random mergers. There are also ultraluminous X-ray sources in nearby galaxies that once puzzled astronomers. Their brightness exceeds that expected from stellar mass black holes fed at normal rates. Some of these sources have now been identified as neutron stars with extremely strong magnetic fields, while others are good candidates for intermediate mass black holes. This shows that the boundary between different compact objects is more complex than once believed. Black holes help test the constancy of physical laws. The precise shape of their shadows and the details of gravitational wave signals constrain alternative theories of gravity. So far, all high-precision tests agree with general relativity, even in strong gravity regimes very different from the solar system where the theory was first tested. Each confirmation narrows the space for competing theories and increases confidence in our current understanding. The surroundings of black holes produce natural laboratories for plasma physics. The matter in accretion disks is ionized, threaded by magnetic fields, and moving at relativistic speeds. This combination produces synchrotron radiation, strong polarization signals, and rapid variability. Observations of polarization near M87* have already revealed ordered magnetic fields shaping the inner flow, directly linking theoretical predictions with real data. In terms of cosmic energy output, accreting supermassive black holes are among the brightest persistent sources in the universe. Active galactic nuclei and quasars dominate the radiation background in some wavelengths and can be seen across billions of light years. Their spectra contain broad and narrow emission lines that reveal gas velocities of thousands of kilometers per second, allowing estimates of black hole mass and accretion rate. Finally, catalogs of black hole mergers are growing every year. Each new detection adds a point to the distribution of masses, spins, and redshifts. Patterns are beginning to emerge, such as possible preference for certain mass ranges or hints of hierarchical mergers where black holes are built up step by step. These statistical studies turn individual dramatic events into a population-level understanding of how black holes form and evolve across cosmic history. Sometimes a star wanders too close to a massive black hole. At first, nothing unusual seems to happen. The star follows its orbit, slowly curving toward the center of the galaxy. But as it approaches, the difference in gravity between its near side and its far side becomes stronger. This is tidal gravity, the same effect that creates tides on Earth, but on a far more extreme scale. There is a special distance called the tidal radius. If the star crosses this distance, gravity from the black hole pulls more strongly on the side closer to it than on the side farther away. The star is stretched into a long stream. Its internal gravity can no longer hold it together. In a short time, the star is torn apart. This event is called a tidal disruption event, or TD. What happens next is dramatic, but follows clear physics. Roughly half of the stellar material is flung outward into space. The other half remains gravitationally bound to the black hole. That bound gas falls back toward the center, forming a temporary accretion disk. As the gas spirals inward, it heats up to millions of degrees and emits intense ultraviolet and X-ray light. From Earth, this appears as a sudden bright flare in a quiet galaxy that slowly fades over months or years. Astronomers have now observed dozens of confirmed tidal disruption events. They are identified through their light curves, which rise quickly and decline in a characteristic way, and through their spectra, which show broad emission lines from rapidly moving gas. By measuring how fast the light fades and how hot the gas becomes, scientists can estimate the mass of the black hole responsible. The black hole does not eat the star instantly. The debris follows elongated orbits. Some returns to the black hole days or weeks after the disruption. The rate at which gas falls back determines how bright the event is. The fallback rate usually follows a predictable curve, dropping roughly as the inverse of time to the power of 5/3. This mathematical pattern matches many observed events, showing that the basic theory is correct. In some tidal disruption events, powerful jets are launched. Material near the black hole is accelerated to speeds close to the speed of light and focused into narrow beams. When one of these beams is pointed near our line of sight, the event appears extremely bright, even across billions of light years. These are called jetted TDs and produce strong emission in X-rays and gamma rays. Tidal disruption events also reveal where black holes are hiding. Many galaxies have quiet centers with no obvious signs of an active nucleus. When a TD flares in such a galaxy, it betrays the presence of a central massive black hole that was previously undetected. In this way, destroyed stars become probes of otherwise invisible black holes. There is a limit to which stars are disrupted. For supermassive black holes above about 100 million solar masses, the tidal radius lies inside the event horizon. In those cases, a star could fall in whole without being torn apart where we can see it. This means TDs are most common around black holes of intermediate supermassive size, where the tearing occurs outside the horizon and produces visible light. Supercomputer simulations have reproduced tidal disruption events in detail. They show the star stretching into a long filament, looping around the black hole, colliding with itself, and forming a hot disk. The simulated light curves and spectra match real observations with increasing accuracy. Each improvement in simulation adds new clues about turbulence, magnetic fields, and how gas behaves under extreme gravity. Tidal disruption events connect violent astrophysics with precise measurement. They give direct evidence of strong gravity in action, reveal hidden black holes, test theories of accretion, and allow estimates of black hole masses. They also remind us that galaxies are not static systems. Stars move, orbits change, and sometimes a single close passage ends in the creation of one of the brightest flares in the universe. Tidal disruption events do not all look the same. Their appearance depends on both the mass of the black hole and the structure of the star that is being torn apart. A compact star like a white dwarf behaves very differently from an extended giant star. The density profile inside the star affects how the debris is spread in space and how quickly gas falls back toward the black hole. This means that by studying a TD carefully, astronomers can learn not only about the black hole, but also about the kind of star that was destroyed. The geometry of the encounter also matters. If the star passes almost directly through the tidal radius, it can be fully disrupted. If the passage is more distant, the star may only be partially stripped, losing its outer layers while the core survives and returns for another orbit. These are called partial disruption events. In these cases, the same star can be damaged multiple times, each close passage producing a smaller flare. Observations of repeating flares in some galaxies suggest that partial disruptions really do occur. The debris from a TD does not immediately settle into a smooth disk. At first, it forms long streams that collide with themselves when they loop around the black hole. These collisions are important because they convert orbital energy into heat and help circularize the orbits, turning the chaotic stream into a more regular accretion flow. The details of these collisions control how bright the event becomes and how long it lasts. Dust and gas around the black hole can also reprocess the light. High-energy radiation from the inner regions is absorbed by surrounding material and then re-emitted at longer wavelengths, such as optical or infrared. This creates an echo of the original flare that can be seen long after the high-energy emission fades. By comparing the timing of these echoes at different wavelengths, astronomers can map the structure of the region around the black hole in 3 dimensions. Some tidal disruption events occur in galaxies with strong magnetic fields or with previous black hole activity. In these environments, the flare interacts with pre-existing gas and can drive powerful outflows. These winds carry material away at thousands of kilometers per second. Spectra of TDs often show signatures of these fast winds, such as broad absorption features indicating gas flowing toward or away from us along the line of sight. The chemistry of the disrupted star is also revealed. As the star is pulled apart, its inner layers are exposed. Elements such as carbon, oxygen, nitrogen, and heavier products of stellar fusion leave fingerprints in the light emitted by the debris. In this way, TDs act like natural laboratories for stellar interiors, letting us see material that would normally be hidden deep inside a star. Tidal disruption events also provide a way to measure black hole spins. The shape of the debris disk and the precession of orbits are influenced by the rotation of the black hole through relativistic frame dragging. Subtle periodic variations in the light curve may carry information about that spin. This is still an active area of research, but in the future, large samples of TDs may become one of the best methods for measuring how fast supermassive black holes rotate. Not all TDs happen at galaxy centers. Some may occur in star clusters where an intermediate mass black hole resides. Evidence for these intermediate black holes is still developing, but TDs can act as signposts. A bright flare in a dense star cluster without an obvious galactic nucleus may signal the presence of such a hidden black hole with a mass between that of stellar and supermassive ones. The rates of TDs are another important clue. Current estimates suggest that in a typical galaxy, a star is fully disrupted by the central black hole roughly once every 10,000 to 100,000 years. Individual galaxies are therefore quiet for long stretches, but across the whole universe, with billions of galaxies, many tidal disruptions are happening at any given moment. Modern wide-field surveys are beginning to catch dozens per year. Future telescopes, such as the Vera Rubin Observatory, will scan the entire visible sky every few nights. This will dramatically increase the number of detected tidal disruption events and will allow scientists to follow their early stages in detail. Catching a TD just days after the disruption provides unique information about the first shocks and the initial formation of the accretion disk. In summary, tidal disruption events are not only spectacular, they are rich in information. They reveal hidden black holes, map their environments, expose the interiors of stars, launch jets and winds, and test the laws of gravity in strong fields. By watching a star torn apart, we learn about both the star and the black hole, and about the complex dance of matter and gravity at the edge of the ultimate one-way boundary. Before we could observe black holes directly, much of what we knew about them came from mathematics. Today, we go one step further. We build entire virtual universes inside supercomputers and place black holes in them to see how they behave. These simulations do not replace observation. Instead, they act like laboratories we cannot build in real life. A simulation begins with the basic laws of physics. Einstein's equations of general relativity describe gravity. The equations of fluid dynamics describe how gas flows. Plasma physics describes how charged particles respond to magnetic fields. All of these are turned into numerical instructions that a computer can follow step by step. The computer then evolves a model universe forward in time, sometimes for billions of simulated years. Cosmological simulations such as Illustris, Eagle, or TNG include dark matter, gas, stars, and black holes from the early universe onward. In these virtual universes, Black holes are allowed to grow by swallowing gas and by merging with other black holes during galaxy collisions. As they grow, they release energy in the form of radiation and jets. This feedback pushes gas away or heats it, changing how many new stars can form. When the result of the simulation ends up looking like real galaxies and clusters that we observe in the sky, it is a strong sign that the underlying physics is on the right track. Simulations can zoom in as well. Instead of an entire galaxy, they can focus on just the region near one black hole. High-resolution models track the motion of gas streamlines, the twisting of magnetic fields, and the formation of hot spots in accretion disks. These hot spots may explain the rapid flickering seen in real observations. They also help predict the pattern of polarization in light, which tells us how magnetic fields are arranged close to the event horizon. Numerical relativity is another powerful branch of simulation. It focuses directly on Einstein's equations without approximation. When two black holes spiral together and merge, space-time itself is strongly curved and analytic solutions are impossible. Supercomputers solve the equation step by step, producing the exact waveform of gravitational waves expected from the merger. When detectors such as LIGO and Virgo see the same waveform in real data, it is a spectacular confirmation that both the simulation and the theory are correct. Simulations also help us explore ideas that cannot yet be tested observationally. They can include hypothetical forms of matter, modified gravity, or different initial conditions in the early universe. By comparing the virtual sky with the real one, scientists can rule out some possibilities and keep others alive. In this way, simulations act as filters that separate ideas that work from those that do not. One of the advantages of a virtual universe is that it can be paused, rewound, or inspected from any angle. Researchers can follow a single black hole from its birth in the collapse of a massive star to its growth inside a galaxy and eventually to its merger with another black hole. They can measure its mass, spin, and environment at every moment. This long-term view is impossible to obtain with a telescope alone, since real cosmic evolution happens over millions or billions of years. Even the famous images of black hole shadows are guided by simulation. Before observing M87*, scientists generated thousands of synthetic images using different models of disks, jets, and magnetic fields. These simulated images were then processed in the same way that the real radio data would be processed. This allowed astronomers to understand what features were reliable and which were artifacts of the observation method. When the real image was finally produced, it could be compared directly with the library of virtual ones. In the future, simulations will become even more detailed. Faster computers and better algorithms will allow smaller structures, more realistic physics, and longer simulated times. They will include radiation transport, more complete chemistry, and fully relativistic magnetized plasmas. As observations improve, especially with new gravitational wave detectors and sharper black hole images, simulations and data will move closer together until the virtual universe and the observed one can be compared pixel by pixel and waveform by waveform. Simulations do not make black holes less mysterious, but they make them more understandable. They let us watch events too slow, too fast, too distant, or too dangerous to observe directly. By creating virtual black holes and entire virtual galaxies, we learn how the real universe works. In a sense, we build small universes on Earth in order to understand the vast one that surrounds us. The idea of life near a black hole sounds like pure science fiction, but it can be explored with real physics. A black hole is not automatically destructive at large distances. Far enough away, its gravity acts just like the gravity of any other object of the same mass. A planet could orbit a black hole in a stable path the same way Earth orbits the Sun, provided the orbit is outside the dangerous region near the event horizon. The most important condition for life is not the nature of the central object, but the source of energy. Around an isolated black hole without a companion star, darkness would dominate. However, energy could still come from several places. A nearby star could warm orbiting planets, just as our sun warms Earth. A glowing accretion disk around the black hole could also provide powerful radiation, although that environment would likely be harsh and variable. Even geothermal energy from a planet's interior could in principle support subsurface ecosystems, as happens with some organisms on Earth. A planet near a black hole would see an unusual sky. Because gravity bends light, stars behind the black hole would appear stretched into arcs or duplicated in strange patterns. A bright ring called the photon ring would mark paths of light that almost circle the black hole before escaping. The black hole itself would not be completely black to the observer, but would cast a perfectly dark circular shadow against a warped, luminous background. The night sky would look like a cosmic funhouse mirror. Time would also behave differently. Clocks near the black hole run more slowly compared with clocks far away. If intelligent beings lived near such a world and exchanged signals with distant civilizations, they would notice that much more time passes in the distant universe than on their own planet. To them, history outside would seem to move faster, while locally everything would feel normal. This effect is not psychological. It is a real consequence of general relativity. Tidal gravity represents another challenge. If a planet's orbit is too close, gravity on its near side would be significantly stronger than on its far side. This could stretch and stress the planet and its oceans. For supermassive black holes, however, the tidal forces at the event horizon are actually weaker than those near small black holes, because the curvature changes more gently over large distances. This means that, paradoxically, a very large black hole can be less tidally dangerous close to its horizon than a small one is. Habitability would depend on radiation levels. Accretion disks and jets around active black holes produce intense X-rays and gamma rays that can strip atmospheres and damage biological molecules. To remain habitable, a planet would either need protection, such as a strong magnetic field and thick atmosphere, or it would have to orbit a dormant, quiescent black hole with little surrounding activity. In that case, the environment might actually be quite calm, with the black hole acting mainly as an invisible gravitational anchor. There is also the concept of a rogue planet captured by a black hole. Planets that drift through interstellar space without a star might eventually fall into wide orbits around a black hole. Such planets would be cold at the surface, but internal heating from radioactive decay and tidal flexing could maintain subsurface oceans beneath thick ice layers. On Earth, life exists around deep-sea vents without sunlight, so similar forms might be possible on such distant worlds. Communication and astronomy from such a planet would be fascinating. Signals sent outward would be redshifted by gravity, losing energy and stretching in wavelength. Light from distant galaxies would appear altered by both gravitational lensing and time dilation. Civilizations there would develop science under very different visual and temporal conditions, yet the same physical laws would still apply. Life near a black hole is therefore not impossible by known physics. It is simply unusual. Stable orbits are possible. Energy sources exist. Protection from radiation is a challenge, but not inconceivable. The biggest difference would be perception. Skies would be distorted, time would not match the rest of the universe, and gravity would shape both the environment and the culture of any civilization that arose there. Thinking about life near a black hole reminds us that habitability is broader than a planet like Earth around a star like the Sun. It depends on energy, chemistry, and stability, all of which can, in principle, exist in many cosmic settings. Black holes, often imagined only as destroyers, could also be quiet neighbors around which worlds slowly orbit in dark, strange, but physically consistent environments. Life near a black hole would not only face physical challenges, but also experience a very different sense of place and time. One of the most striking effects is gravitational time dilation. The closer a planet is to the black hole, the slower time passes for everything on that world compared with distant regions. A civilization living there could watch the distant universe evolve faster than its own history. Stars would age, galaxies would change, and even cosmic expansion would progress more rapidly in the outside cosmos than in their own local frame of reference. Daily life would also be influenced by gravity. On Earth, gravity is nearly constant from one location to another. Near a black hole, especially a smaller one, gravity can change noticeably over relatively short distances. Mountains, oceans, and even planetary crusts would respond to these tidal forces. A planet that is too close might experience strong internal heating, earthquakes, and tides much larger than those on Earth. In some cases, these forces could melt ice layers or drive volcanic activity, creating both hazards and potential sources of energy. Light would not travel in straight lines. Beings living there would see multiple images of the same star in different parts of the sky. A bright ring around the black hole, created by photons looping almost completely around it, would be a permanent feature of the heavens. Eclipses and transits would look very different because gravitational lensing would distort the apparent shapes of objects passing behind the black hole. The concept of day and night could also change. If the main source of light were an accretion disk, the illumination might flicker or vary as gas spiraled inward. Instead of regular cycles like those on a planet orbiting a star, the sky might glow with a soft, shifting radiance punctuated by bursts and flares. Even in a quiescent system, any nearby star would trace unusual paths in the sky because of the strong curvature of space-time. Technology in such an environment would require careful engineering. Satellites in orbit near a black hole would need to account for relativistic effects. Navigation systems would have to correct for gravitational redshift and time dilation to synchronize clocks and communication networks. Space travel between regions with different gravitational potentials would involve not just changes of position, but changes of experience time as well. Psychologically, the awareness of time running differently elsewhere might shape culture. A journey outward to a region of weaker gravity and back again would mean returning to a future in which many more years had passed for others. Stories, relationships, and historical continuity would be influenced by this asymmetry. What we treat as science fiction time travel would be an everyday reality created simply by moving through curved space-time. Despite the difficulties, such a place could still be scientifically rich. A civilization living near a black hole would have a front-row view of extreme physics. They could study accretion disks, jets, strong gravitational lensing, and tidal disruption events as common natural phenomena in their sky. Their understanding of gravity and space-time might develop earlier than ours simply because the evidence would be all around them. If life evolved there from the beginning, it would likely adapt to darkness, variable light, and stronger gravitational gradients. Its biology might rely less on sunlight and more on geothermal or chemical sources of energy. Eyes, if present, might evolve to interpret distorted visual fields, or other senses might become dominant. Evolution would respond not to our familiar Earth conditions, but to the unique environment created by the black hole's gravity. Considering life near a black hole expands our sense of what is possible. It reminds us that the universe is not limited to sun-like stars and Earth-like planets. Gravity, energy, and chemistry can combine in many different arrangements. Some of those arrangements may be strange to us, but they are still governed by the same physical laws. A black hole, instead of being only an agent of destruction, could be the silent center of a system where worlds orbit, time flows unevenly, and life slowly adapts to the deepest curvature of space-time. Black holes are often imagined as endlessly hungry objects that can grow without limit. In reality, their growth is strongly constrained by the laws of physics. Gravity may be powerful, but it is not the only force at work. Radiation pressure, angular momentum, magnetic fields, and the structure of the surrounding galaxy all place limits on how fast and how large a black hole can become. By studying these limits, we learn not only about black holes themselves, but also about the evolution of galaxies and the history of the universe. One of the most important limits is called the Eddington limit. When gas falls toward a black hole, it heats up and emits light. That light carries momentum. Photons, although massless, push on matter. If the black hole accretes too quickly, the outward pressure of radiation becomes strong enough to balance the inward pull of gravity. At that point, the inflow stalls. The Eddington limit therefore sets a maximum steady luminosity and, indirectly, a maximum steady accretion rate. For a given black hole mass, there is a characteristic brightness beyond which material is blown away rather than swallowed. This limit explains why black holes cannot simply double their mass overnight. Even under ideal Eddington-limited accretion, growth follows an exponential timescale known as the Salpeter time, roughly tens of millions of years. Over cosmic history, this timescale is short enough to allow the formation of very massive black holes, but long enough that their growth is gradual rather than explosive. If we see a black hole that is extremely massive, it must have either accreted close to the Eddington rate for a long time, or formed from a fairly massive seed. However, nature is rarely perfectly steady. Some systems appear to exceed the Eddington limit for short periods. These are called super-Eddington accretors. In them, geometry matters. If radiation can escape along certain directions while matter falls along others, the effective radiation pressure on the inflowing gas may be reduced. Thick accretion disks, funnels, and strong magnetic fields can all channel the flow in ways that allow temporary violations of the simple spherical Eddington picture. Even so, on long timescales, the average accretion rate tends to remain limited by radiation feedback. Another limit comes from angular momentum. Gas in galaxies does not fall straight into black holes. It has orbital motion. Angular momentum acts like a barrier, forcing matter to spiral inward gradually through an accretion disk. Friction within the disk, created by turbulence and magnetic fields, transports angular momentum outward while mass moves inward. This transport is not infinitely efficient. As a result, the rate at which gas can lose angular momentum and reach the black hole is naturally limited. Even in the absence of radiation pressure, disks cannot feed black holes arbitrarily fast. Black hole spin also plays a crucial role. A rotating black hole drags space-time around with it, a phenomenon known as frame dragging. Spin affects the innermost stable circular orbit and therefore changes how much energy can be extracted from infalling matter. There is, however, an upper limit to spin. If a black hole were to reach exactly maximal spin, further accretion of matter with prograde orbits would tend to spin it down. Emission of gravitational waves and magnetic torques also act to limit extreme rotation. Observations suggest that while many black holes spin rapidly, they do not reach the absolute theoretical maximum. Mass itself is limited in different ways depending on the formation channel. Black holes created by the collapse of massive stars cannot have arbitrary masses. Nuclear physics sets a limit on neutron star stability. In parent stability, supernovae disrupt stars in a certain mass range before they can collapse. This creates a predicted mass gap where stellar origin black holes should be rare. Gravitational wave observations are beginning to probe this region, testing whether nature truly respects this theoretical gap or finds ways around it, such as hierarchical mergers of smaller black holes. Supermassive black holes at galactic centers face different limits. Their growth depends on the supply of gas within the galaxy. Feedback from the black hole itself can shut down that supply. As a black hole accretes and shines brightly, its radiation injects heat or expels surrounding gas. This reduces the amount of material available for further accretion. The process creates a self-regulating system. Feed the black hole too efficiently, and it starves itself by clearing its own fuel. This feedback helps explain the observed relationship between the mass of central black holes and the properties of their host galaxies. Galactic environment also matters. In small galaxies, gas can be easily blown out by supernova explosions or by the black hole's own activity. In large galaxies and clusters, gravity holds gas more tightly, allowing black holes to grow more. This leads to a cosmic ecology where the largest black holes tend to live in massive galaxies with deep gravitational wells, while smaller galaxies host modest black holes or none at all. The distribution of black hole masses we observe today is therefore shaped by both local physics near the event horizon and large-scale structure of the universe. Accretion is not the only way black holes grow. They can also merge with other black holes. When galaxies collide, their central black holes sink toward the center of the merged system through interactions with stars and gas. Eventually, they form a binary and spiral together through the emission of gravitational waves. This process is efficient but not instantaneous. It can stall if there is not enough surrounding matter to carry away angular momentum, a problem known as the final parsec problem. Interactions with gas disks and stars probably solve this in many cases, but again the process takes time and places an effective limit on how quickly mergers contribute to growth. Even after black holes merge, gravitational waves carry away some of the system's energy and momentum. In some mergers, the emission is asymmetric, giving the remnant black hole a kick. If the kick velocity is large enough, the black hole can be displaced from the galactic center or even ejected from the galaxy entirely. Ejected black holes cannot easily continue growing because they are removed from dense gas reservoirs. Thus, gravitational wave recoil acts as another indirect limit on long-term growth. In the very distant future, another limit becomes important: Hawking radiation. On human and galactic timescales, this effect is negligible, but in principle it ensures that no black hole lasts forever. Over unimaginably long periods, isolated black holes slowly lose mass by emitting radiation created by quantum effects near the horizon. Smaller black holes evaporate faster, while supermassive ones take far longer than the current age of the universe. Although Hawking radiation does not limit present-day growth, it completes the picture by showing that black holes are not perfectly permanent. The cosmic microwave background also sets a subtle boundary. In the early universe, the background radiation was hotter. Small black holes immersed in that hot radiation could gain mass faster than they lost it by Hawking radiation. As the universe expanded and cooled, the balance shifted. Today, only extremely tiny black holes would evaporate significantly, while stellar and supermassive black holes overwhelmingly gain mass through accretion and mergers. The thermal history of the universe therefore influences which black holes can survive and how they evolve. Putting these pieces together, we see that black holes are not simple vacuum cleaners that consume everything around them without resistance. Their growth is regulated by radiation pressure, angular momentum, spin limits, feedback into their host galaxies, merger dynamics, and even quantum effects. This self-regulation explains why we do not see black holes of arbitrary size everywhere, but instead a structured population with typical mass ranges and clear correlations to their environments. Understanding these limits is essential for cosmology. The timing of black hole growth influences when galaxies stop forming stars, how heavy elements are distributed, and how the large-scale web of cosmic structure evolves. Each new observation, from X-ray telescopes to gravitational wave detectors, refines our understanding of these limits and tests whether our theoretical picture is correct. Black holes, then, sit at the intersection of extremes. They are the densest objects known, but they cannot grow without bound. They are powered by gravity, yet limited by light. They are shaped by their own feedback, by the galaxies that host them, and by the expanding universe itself. Their limits are not signs of weakness. They are signatures of deep physical laws that connect the smallest scales near the event horizon with the largest scales of cosmic structure. Imagine approaching a black hole not as a sudden catastrophe, but as a long journey. From far away, nothing would seem unusual. The black hole would be invisible unless it had a bright disk of gas around it. Space would appear dark and ordinary, filled with familiar stars. Only the slow drift of surrounding objects toward a common point would hint that something massive was present. Gravity does not announce itself with drama at great distances. It is subtle, quiet, and patient. As you come closer, the first noticeable change is not motion but sight. Light from stars passing behind the black hole bends around it. The sky begins to distort as if reflected in a curved mirror. Constellations stretch, twist, and duplicate. A star that should be behind the black hole appears again on the other side, because its light has taken a path around the gravitational well. The black hole does not simply block light. It warps the entire view of the universe. At some point, the shadow becomes obvious. It is not a solid surface, because black holes have none. It is a perfectly dark circle against the background of warped starlight. Around it, a bright and thin ring appears, created by photons that almost orbit the black hole before escaping. This photon ring is not a physical object. It is the geometry of space-time made visible. Approaching it feels like coming toward the edge of a hole in the sky rather than a hole in matter. If the black hole has an accretion disk, the scene becomes even more striking. A glowing, flattened swirl of gas circles the darkness. One side of the disk appears brighter than the other. This is not because the gas itself is different, but because of relativity. Light from the side rotating toward you is boosted in energy, while light from the side rotating away is diminished. The disk seems to curve upward and downward at the same time, wrapping around the black hole like a halo, because your line of sight bends with the curvature of space-time. Time begins to reveal its strangeness as well. Your own clock runs normally for you, but signals exchanged with distant observers show a growing difference. From their perspective, your actions slow down as you approach the black hole. Every movement, every heartbeat stretches in time. From your perspective, however, their world accelerates. Distant processes, cosmic events, and even civilizations seem to speed ahead as your gravitational time dilation increases. Time does not break, but it stops being universal. The feeling of gravity depends strongly on the size of the black hole. Near a stellar mass black hole, tidal forces change rapidly over small distances. Your feet would feel a much stronger pull than your head. This difference stretches objects into thin shapes, an effect often called spaghettification. Near a supermassive black hole, the same gradient can be gentle even close to the horizon. You could, at least in principle, cross the event horizon without feeling anything remarkable at that instant. The danger lies not in the crossing, but in the inevitability of what follows once inside. Sound is absent in most of this environment. Space is nearly vacuum, offering no medium for ordinary sound waves. The silence is absolute. If you are near an accretion disk or inside a cloud of gas, compression waves could exist, but they would not resemble familiar acoustic sensations. Instead, the dominant sensory experience is visual and temporal, distorted light and distorted time. As you move closer still, the night sky becomes stranger. The region directly behind you shrinks into a small, bright patch. The rest of the universe seems to wrap around the black hole ahead. It becomes increasingly difficult to say what is in front or behind, because space-time itself is curved. Straight lines in this geometry do not look straight. Your intuition, trained by life on Earth, ceases to be reliable. Crossing the event horizon is unlike any boundary you know. There is no physical surface, no sudden impact. From your own frame, you simply continue falling. The horizon is a mathematical surface that marks the place where escape is no longer possible. Light emitted inward can still reach you. Light emitted outward never will. Causality narrows. The future ceases to include any possibility of turning back. It is not a wall, but a one-way seam in space-time. If the black hole is rotating, the experience becomes even more complex. Rotation drags space-time around with it, creating a region called the ergosphere outside the horizon. Inside this region, everything is forced to rotate with the black hole, even light itself. You cannot remain perfectly still relative to distant stars. Space is literally being pulled along. Energy can, in principle, be extracted from this rotation through processes that split particles and redirect momentum, though surviving such an event is beyond practical reality for human travelers. Close to the singularity, classical descriptions of experience become unreliable. Infalling matter is compressed, heated, and accelerated to extreme energies. Tidal forces grow without limit in theoretical models based on general relativity. Whether a true point of infinite density exists is unknown. Quantum gravity, a theory not yet completed, will likely replace singularities with something finite but still extreme. From your personal perspective, however, the final approach would be brief, irreversible, and hidden from the external universe by the horizon. Outside observers never see you reach the horizon. Instead, they see you slow and fade, your light redshifted to longer and longer wavelengths. To them, you seem to freeze, suspended just above the shadow. To you, nothing special happens at that moment. Crossing the event horizon is unlike any boundary you know. There is no physical surface, no sudden impact. From your own frame, you simply continue falling. The horizon is a mathematical surface that marks the place where escape is no longer possible. Light emitted inward can still reach you. Light emitted outward never will. Causality narrows. The future ceases to include any possibility of turning back. It is not a wall, but a one-way seam in space-time. If the black hole is rotating, the experience becomes even more complex. Rotation drags space-time around with it, creating a region called the ergosphere outside the horizon. Inside this region, everything is forced to rotate with the black hole, even light itself. You cannot remain perfectly still relative to distant stars. Space is literally being pulled along. Energy can, in principle, be extracted from this rotation through processes that split particles and redirect momentum, though surviving such an event is beyond practical reality for human travelers. Close to the singularity, classical descriptions of experience become unreliable. Infalling matter is compressed, heated, and accelerated to extreme energies. Tidal forces grow without limit in theoretical models based on general relativity. Whether a true point of infinite density exists is unknown. Quantum gravity, a theory not yet completed, will likely replace singularities with something finite but still extreme. From your personal perspective, however, the final approach would be brief, irreversible, and hidden from the external universe by the horizon. Outside observers never see you reach the horizon. Instead, they see you slow and fade, your light redshifted to longer and longer wavelengths. To them, you seem to freeze, suspended just above the shadow. To you, nothing special happens at that moment. Reality diverges depending on the frame of reference. Both descriptions are valid within relativity. They simply correspond to different viewpoints in curved spacetime. The presence of jets adds another layer to this environment. Magnetic fields twisted by rotation can launch beams of particles near light speed from the poles of the black hole. If you were positioned along one of these axes, the sky would blaze with narrow, intense streams of radiation. These jets stretch for thousands or even millions of light years and can outshine entire galaxies. They connect the smallest scales near the horizon with vast cosmic distances. The colors you would see depend on redshift and blue shift. Light falling deeper into the gravitational well is pulled toward redder wavelengths. Light emitted from material rushing toward you is pushed toward bluer, higher energy wavelengths. A dynamic mosaic of changing colors surrounds the black hole as hot gas orbits rapidly, producing flickers and flares that reflect the complex motion of turbulent plasma. Navigation near such a place is extremely challenging. Ordinary straight-line travel no longer corresponds to shortest paths. To follow a safe orbit, you must account for both gravitational attraction and spacetime curvature. A small mistake in velocity or direction can shift you from a stable orbit into a fatal plunge or a wild escape trajectory. Spacecraft computers in this environment would need to solve relativistic equations continually merely to maintain position. Emotionally, the experience would likely feel overwhelming. The combination of silence, distorted stars, slow personal time, and a perfectly dark center in the sky creates a sense unlike any landscape in the universe. There is awe, but also inevitability. Black holes do not pursue or attack. They simply curve space-time so strongly that falling becomes the only future available inside a certain region. Yet the environment near a black hole is not purely destructive. It is also creative. Accretion disks shine brighter than almost any other object in the cosmos. Jets seed intergalactic space with particles and magnetic fields. The violent physics near horizons shapes galaxies and influences the structure of the universe on the largest scales. Standing near a black hole, if one could do so safely, would be standing at one of the engines of cosmic evolution. As you drift away again in imagination, the distortions relax. The sky returns to familiar shapes. The black shadow shrinks to a point, then to invisibility. Constellations straighten. Time differences remain, recorded forever in clocks that experience different gravitational potentials, but your intuitive sense of ordinary space returns. The universe feels flat again, even though you now know that unseen wells of curvature lie scattered among the galaxies. What it is truly like near a black hole is not defined by terror, but by difference. Light, time, motion, and direction behave according to deeper rules than everyday experience reveals. The laws are strict, but they are not malicious. They simply express the geometry of gravity at its strongest. To stand near a black hole is to witness those laws written across the sky, to see space-time curve into a shape the human eye is not evolved to expect, and to recognize that beneath every familiar surface of the universe lies a deeper and stranger order. If you made it this far, thank you for being here. If this helped you relax, consider leaving a like and subscribing. I'll keep making more content like this.